Well, hello students. Did you miss me? Are you missing me now? I knew you would miss me. Thank you for making my day. Alright, we are going to do lesson 10.2. This is out of your book. This is graphing parabolas. Again, I am assuming you have all seen this in Algebra 1 and Algebra 2, so we're going to move, I don't want to say super fast, but we're going to cut to the chase here in a minute. So I want to remind you to start out with graphing a parabola, the parent function y equals x squared, and how the graph of this looks. And again, if you didn't know, we just start with a t-table. So if x is -3 quantity squared, -3 times -3, you all know that, right, is 9. And -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. So if I look at the graph of the parabola, again, this shouldn't be anything new to y'all. If each one of these ticks are 1, 1, 2, 3, 4, 5, we have 1, 1, -1, 1, there's 0, 0, down here. 2, 4 was up here, and 3, 9 is pretty off the charts, but it's up there. So the that was horrible. Let's do that again. The parabola looks like, yay. We're going to learn some pretty cool properties of parabolas in a minute here too. Okay, a couple things about the parabola before we move on. Right here, this spot is called the vertex, and it's the lowest point, the minimum value in this parabola. And right here, straight down the middle, is, in this case, what we're going to call the axis of symmetry, because it is purely exactly symmetric about, in this case, the line x equals 0. So that's going to be our axis of symmetry, and if you see, the axis of symmetry goes straight through the vertex, right there. So the vertex is always on the axis of symmetry, and the axis of symmetry always contains the vertex. So, surprised by that, weren't you? So what if I had to graph something like f of x equals x squared plus 4? How does that change my parabola from before? That wasn't straight. Let me do that one again. Well, how does this change? Well, I'm going to start out here in, which color should I use? Anyone have an idea? A suggestion? Orange, great color. Thanks. So if this here is a rough sketch of the parent function x squared, what does x squared plus 4 do? Well, what it's going to do is what we're going to be doing is we're going to be adding 4 units to every value of x we already had. So that is where this vertex before was at 0, 0, it's now at 0, 4. And where this point, which was at 1, 1, is now at 1, 5. And same thing here, I'm just adding 4 units to the y values. For instance, at 2, on the graph here, sorry, it's not drawn to scale, but you know, you can hang. We had 2, 4 is a point on the parent function. Well, add 4 points to the y value, 2, 8, somewhere up here is going to be on my new function. So this is what we call a vertical shift, in this case up 4 units. So this is my x squared plus 4. Okay, well, what's different now between something like f of x is going to equal x minus 4 quantity squared? Sorry, let me try that again. X minus 4 quantity squared. What does that do? Well, let us again start with our parent function. Let me try to do a little bit better of a job. Let me just see what happens here real quick. Nope, nope, nope. Yeah, that's nice. Let me erase that line too. Okay, so let's look at, let's call this the x-axis right here. Excuse me, yeah, y-axis that is, and we'll call this the x-axis. And let's, again, let me start with my parent function, x squared, so, 2, 4, and 2, 4, and then I'm just going to kind of imagine where this goes up from here. Yeah, that was horrible. Let's try that again. Okay, so what does this minus 4 now in parentheses do? Now notice the difference between, again, what we had here. We had x squared plus 4. That is, we take our value of x, we square it, then add 4. But if you notice here, we take our value from x, then subtract 4 from that value, and then square it. So I can already see here, maybe if I made a little t-table off to the side here, that, what's a good color today? Blue. If I just put in 0 for x, that would actually get me negative 4 squared. That'd be 16. What I usually like to do is think in this expression, remember how our vertex is here is at 0, 0? What do I have to do to make y 0 here in this case, or f of x 0, or y value 0? Well, whatever this inside my square function here has to equal 0. That is, like this x minus 4 has to equal 0. And where does x minus 4 equal 0? What, solve for x? X equals 4. So 1, 2, 3, 4. So what I've just had to do is, if it's inside the parenthesis here, I'm going to end up shifting it right 4 units. And again, why? Because I kind of need 4 more units of x to make what's inside this parentheses there 0. And if I put in 5 now for x, I'd have 5 minus 4, which is 1, 1 squared. And if I put in 3 in for x, I'd have 3 minus 4, negative 1 squared. Negative 1 quantity squared is here. So check it. What did that all do? Again, that minus 4 now was a right shift. And let's just, on the same happy graph there, let's maybe try, I've been dying to say this. Yeah, Van Dyke Brown. Let's pull out a Van Dyke Brown. So if I get a Van Dyke Brown here, I'm just going to put this function here in the corner. What if I did f of x, it's like Van Dyke Gold, x plus 4 quantity squared? What would change now? Well, again, I have to think what sets that inside equal to 0. It's not going to be positive 4 this time, is it? No, it's, wait, say that again? No, negative 4, yeah, good. So if I'm adding 4 inside the parentheses, I'm not moving it to the right 4 like I'd expect. In fact, if I put in positive 4, I'd have 8 squared, 64. That's off the charts, yo. I have to put in negative 4 to get this inside to be 0. So if it's a plus inside the parentheses, I know intuitively we want to think it moves it to the right, but it actually moves it to the left 4 units. So this here in Van Dyke Brown is going to be f of x equals x plus 4 squared. Alright, well, what if we just did everything in combination? Cool, it's still working. What if I had something like f of x, actually before we get to, excuse me, we'll get to the we'll get to the combination in just a second. What if I did something like f of x equals 3x squared? Oh, Mr. Bustling, you're so crazy. Sorry. Well, what is this going to do? Again, there's my y-axis, there's my x-axis. That was a horrible x-axis. Let's do that again. So see if you can justify what this does. Well, what does this 3 here and do? Again, let's start with, okay, is there any vertical shift? No. Is there any horizontal shift? No. So this vertex should be right there at 0, 0. But again, if I'm not sure, I could always do a t-table. 0, I put in 0, I have 0 squared times 3, which is 0. But if I put in 1, now I'm going to have 3 times 1 squared, which is 3. So that is up at 1 comma 3. And same thing if I put in negative 1. If I put in negative 1, I'll have 3 times negative 1 quantity squared, which is also 3. Okay. Well, what if you put in 2? Well, let's square the 2. That's going to give me 4 times 3 is 12. Whoa, 12. That's off the charts. In fact, lucky now I have this nice little grid back here. I can tell exactly where that is. So what did this 3 in front do? Well, it took all my y values and multiplied it by 3. I'll put the parent function here, y equals x squared, goes at 1, 1, 2, 4, 3, 9, 1, 4, and 3, 9. So this would have been just x squared by itself. You see how that 3 actually ended up making it steeper? It kind of, shrunk it in this way, if you will. Or as I like to think, it's just going up faster. Okay, well, let me just put this on the same chart here. I'll do this in a different color. What if instead, if I were to do something like f of x equals 1/3 of x squared? Okay, well, what is this 1/3 going to do now without making a t-table? Well, remember, for instance here, if it took our original value of 1 and multiplied it by 3, in this case it's going to take our original value at x equals 1 and multiply that y value by 1/3. That's going to be all the way down there at 0, 1/3. And here, right here, where our y value was 4, that's going to now multiply 4 by 1/3, which is 4/3, barely bigger than 1. And just again by symmetry here, same thing on the other side. Yeah. Sorry, I'm having trouble with the... And what about when x equals 3? Well, our original y value was 9, but it's going to take that 9, multiply it by 1/3, and it's going to give us at 3. It's going to give us a y value of 3. So look at that. What did that do? Again, the red was the parent function, the black was 3x squared, and we could see here if this number, this number ended up being less than 1, this ended up kind of making it fatter, if you will, or wider. So if this number that we multiply is bigger than 1, it ends up making the graph steeper or more narrow. And if this number is less than 1, it ends up making it wider. So far, you guys all with me? Good, I'm with you guys all too. Fantastic. So let's just talk real briefly. What if that number is negative? What if instead we did something like f of negative 3x squared? Well, now that it's negative, it's going to take all those original values of x. It's so hard to draw straight. So if this was a negative 3x, it would have taken all my values, say before, let's go back to the positive 3x, the black one, but it's just going to make every value now negative. So instead of a happy face parabola, which started at, it's still starting at 0, 0, right? Clearly we put in 0 for x, we get 0. But if we put in 1, we get negative 3. And if we put in negative 1, we get negative 3. And again, if we put in 2, we got, in this case, negative 12 all the way down here, and vice versa. So that negative sign is going to turn what was a happy face parabola into a sad, smiley, frowny face parabola. So if it's a negative parabola, it's a sad parabola. It's had a hard life. Okay, so now let's put everything together. I'm actually going to get rid of this screen for just a second. So if I have some generic quadratic like this, woo, here we go, getting crazy. Okay, let's see what everything in here does. This is going to move the graph right h units. And you notice how this has to be a minus sign inside the parentheses to go right. If it was a plus, it would go to the left h units. This is going to go up k units. And again, if it's a minus sign, if we're minusing k, then it's going to go down k units. And this is, we just got to be a little careful. It depends if it is. First of all, if it's negative, then it's going to take that happy face and turn it upside down. We're going to get a sad parabola. And if the, I'll say if the absolute value of it is greater than 1, then it's going to become narrower. And if the absolute value of it is less than 1, excuse me, let me fix that inequality sign, then it's going to become wider. And from now on out, we're just going to use these rules to graph the parabola. So you excited? You ready to try one? You ready to try one? What? I can't hear you. Oh, you're not ready? Too bad. We're doing it. And I know usually I'd kind of do a you try at some point, but this being a video lesson, I can't do a you try. So, but you see if you can maybe beat me to the punch here, because I got to set all this up. How would I graph something like 2 times x minus 1 quantity squared plus 3? You guys try this in your notes. You're all taking notes. You better be taking notes. Okay, so when I do this, I start with the vertex. So again, this here is the original vertex at 0, 0. Sorry, hey, there's my original vertex at 0, 0, and let's see what happens here. The minus 1 means it's going to go right 1 unit. And then the plus 3 means it's going to go up 3 units. So I'm right here. That is my new vertex. And a parabola doesn't really have a slope, but I kind of think of if there is a slope, you know that here's the vertex. I'm going to draw this to the side here. And then in the next point of just x squared is 1, 1. I kind of almost think of that little intermediate, like 1, 1, as the slope of a parabola. So that being said, what I'm saying is that if this is my new vertex here at 1, 3, this 2 now is, instead of going up 1 over 1, I'm going to go up 1 over 2 to my next point. And same thing, left 1 over 2. And same idea, if I was going to 2, it would be 2, 4, so I'd go over 2, up 4, but now I'm multiplying that y value by 2, so instead of going over 2, over 4, I'm going to go over 2, up 8, which is, let's see, 1, 2, 3, 4, 5, 6, 7, 8. And again, I'm using my axis of symmetry here. by symmetry, that's going to happen here. And I think these 5 points are going to be enough to, oh, hey, my hand slipped, okay? My hand slipped. To make the parabola. So here is that whole graph, everything included. Again, moving the vertex right 1, up 3, and then moving the slope up 2 units, if you will. Okay, so lucky for you guys, there's one part of this chapter, this section that I'm going to skip, and that is that's using matrices to find a parabola if I give you 3 points, but I just want to briefly talk about it. Nah, I'm kidding. I'll leave it alone. But I did want to talk about the end of your book talks about the geometric definition of a parabola. So parabolas have been known for a long time, and they actually have really, really interesting properties. And if you look around, you could actually see them. And, oops, sorry. Geometrically, hey, go away. Geometrically, what people have noted from early times about a parabola is that there's this special point called the focus. In fact, excuse me, I want to actually just start over. There is a special point called the focus, but here is the actual geometric definition of a parabola. I'm going to take a straight line, might take me a few times, and a point. Now this is what we say a parabola is. A parabola is a set of all points such that the distance from the point, this point we're going to call the focus, F, and this line we're going to call the directrix. Directrix, it's Mr. Shaffian's favorite cereal, you could ask him. The parabola is going to be the set of all points that are the same distance from the point as it is from the line. So the vertex is kind of the special point on there because it's the shortest distance between all of them. That is, the vertex is going to be halfway between the directrix, see if I can do a better job, and the focus. In fact, this distance, we often call this distance between the two P. So that is, it goes up, from here to there. Here, I'm just going to draw this purple line here. And there was that focus. This distance is P from here to there, and this distance from here to there is also P. Well, that's one point, and as I had mentioned, it's all of the points. So I'm going to just draw the parabola now. Here's the parabola. And the idea is if I take any point on the parabola, maybe this point over here, that this point is just as far from the line as it is from the focus, the point F. And it's hard to draw, hard to see exactly, but the idea is that this distance, this green distance, is the same as this distance here, the perpendicular distance from the line. A little hard to tell with my drawing because my art skills aren't perfect, and it's really hard to draw a perfectly good parabola. But that is the geometric definition of a parabola. It is the set of all points, which makes a line, or a smooth curve, excuse me, in this case, such that every single point on this parabola, again, I'll pick another point if you didn't believe me, oh wait, I need a different color. Like this point over here, that the distance from the line, this distance, is the same as that distance. And again, my drawing's terrible. So I'm going to just move screens here and kind of show you in just a second here how we can actually derive the formula of the parabola using the distance formula. Yeah. There's my focus. Okay, so the idea is if I just take any random point on here, I'm just going to call this X and Y, and let's just make our life easier and say that this this is the X and the Y axis, that is the origin here is 0, 0. And this point, the focus, is, we said, P units away. So that is, this point right here is 0, comma, P. And this distance here is also P, this distance. And that actually makes this whole line down here, the gray line, the line y equals negative P, because now it's below the x-axis. Again, the red axis is the x and y axis. So the idea is, if I look at this distance right there, the green distance, it should be equal to this distance right here. So I'm going to call this point xy. This point we call, the focus we called 0p. And this point right here, well, what's the point coordinate of this point? The x value is the same x value as above, because the shortest distance between a point and a line is perpendicular to the line. But the y value on here is negative p, because it's on the negative p line. So I'm going to use the distance formula here to show you how we get the equation of a parabola and why this number p here is going to be important, the distance between the vertex and the focus and or the directrix. So we said that the distance formula, if you guys recall, is going to be our x1 minus x2 quantity squared plus y1 minus y2 quantity squared. Okay, so I'm just going to go back to my graph in just a moment. So if I look at my first x coordinate, so if I call so if I'm looking for it's been a while since I've done this. So what I'm going to do, since these two lines, these two distances are equal, these two green lines, this one and that one, is I'm going to find the distance of them using these x coordinates, xy coordinates here, and these, and I'm going to set them equal to each other. So, excuse me here, I'm gonna just wipe this one clean. I do need the distance formula, but you'll see I'll use them on both sides. So, from the point xy to the focus, my point xy was just xy. The x coordinate for my focus was 0. And my y coordinate was y, but my but my second y coordinate is p. And just to show you where I'm getting these from, I'm going to call this x1, x2, y1, that is, and right now this point's x2, y2, and then I'm going to use this on the other side too. I'll call that one x2 and y2 on the other side. So I'm going to set this equal to, again, this is the distance from the point xy to the focus, and now this is going to be the distance between xy and the point on the directrix. If you recall, the x value didn't change, and then I'm going to have y minus negative p squared. So just cleaning this up, on the left side that gives me x squared plus y minus p, which I'll go ahead and factor out, which is y squared minus 2yp plus p squared. And on the right side I'll clean that up too. X minus x is just 0, and then I'm going to have y minus negative p squared, or y plus p squared. Now that's going to give me y squared 2yp plus p squared. To get rid of the square root, I'm just going to square each side. So I'll have x squared plus y squared minus 2yp plus p squared. And that's going to equal y squared plus 2yp plus p squared. So now I'm going to cancel out what I can cancel out. So if I subtract p from both sides by p, if I subtract y from both sides by y squared, that is, excuse me, by y squared, so I got x squared minus 2yp equals 2yp. I'm going to just solve this in terms of y. So I'll add 2yp to the other side. That'll give me 4yp equals x squared. And lastly, to solve for y, divide by or multiply by 1 by 4p. What just happened? I don't know. Actually, I do know. I know exactly. So we say that we can write a parabola that's centered at 0, 0. Just a heads up, these are always going to be centered at the origin, because you could see if I put in 0 for x, doesn't matter what p is as long as p is not 0. Also would catch on fire. This is going to be our geometric definition of a parabola. So I might have a problem, something like, hey, what? So just for an example, say I have a parabola with a focus at, let's say, 0, 8. Find the what, and maybe part A would ask this question: what is the equation to this parabola? So that's all I know, is that the focus is at 0, 8. So if I look at this geometrically, this focus is all the way up here at 0, 8. It should end up being a fairly steep parabola. Now what this is telling me, that the focus is at 0, 8, is that that's the distance between the vertex and the focus. So p equals 8. So all I have to do is go, y is going to equal 1 over 4p. In this case, p is 8 x squared. And that's going to give me y is going to equal 1 over 32 x squared. I want to just lastly, this isn't in your book, but it's interesting, like, why do we care? Parabolas are interesting. I'm going to put one on its side, and if this is the focus here, what ends up being actually really interesting is that some interesting properties of parabolas. Let's imagine that this is something that reflects. And maybe this is like light coming in. Whenever light comes in, it hits this curve at such an angle that it gets reflected right at the focus. And that doesn't even matter. Maybe the light's coming in like this, it'll go in and get reflected on the focus. Even if it's blink, it'll just go right back in that case. Or maybe just some random, little happy little stray light will just same thing. It's actually and vice versa. Oops. If it was going out like this, it would actually bounce and go perpendicular. So every point ends up hitting the focus. Every light gets bounced and hits the focus. Have you ever, maybe you have a satellite dish. Maybe you're a Dish TV subscriber. Have you ever really looked at your satellite dish? It's not in a circle, it's actually parabolic, and you know that little like thing that's like up there? Guess what that thing right there is? Yeah, it's the focus of the parabolic dish. This is in the shape of a parabola. believe it or not. So the idea is you get all these rays that go out, all these signals, and they hit the dish, and they get reflected in the focus, so they all get magnified. It's pretty cool, don't you think? Or even vice versa, another application of this is your headlights or a flashlight or something like that. Now the idea is kind of reversed. It's a parabolic mirror. And you might have your headlamp like this, but the idea is that the light goes out and you end up focusing it out all into a beam. If you ever looked at a car headlight, it's just a lamp like you might have in your room. But this mirror behind it is in the shape of the parabola, which kind of makes it go out into a beam. Or one last application of this, I know I'm talking your brains out and you're probably done with it. You're like, get on with it. If you're a nerd like me, you like telescopes. And one of the most classic telescopes is called a Newtonian telescope. And it's actually a big tube, and there's a little eyepiece down here. Well, all the way down here at the bottom is actually, you got it, it's a parabolic mirror. There's a couple other mirrors in here. There's one that pretty much goes like this. So the idea is you're out there looking at the stars, and the little light of the star gets in here, goes through your telescope, hits the mirror, and bounces to the focus, which is now at this mirror, and that angles it out this way into your eyepiece. And it's kind of cool because this ends up focusing the light and ends up making it look bigger. And it doesn't matter where that light's coming from. It all gets amplified and magnified into your eyepiece. Pretty cool, right? You never thought you'd learn that in the math class, did you? Okay, well, I hope you enjoyed that. Your homework assignment is posted on the board and your substitute has it. This video will be up live on Plus Portal if you want to watch it again later. And hopefully that wasn't too bad. Probably the hardest part was this whole focus directrix deal. But just keep practicing. Look at the examples in the book. And you got the rest of class to work on your homework, and your substitute's watching you, and he or she is making sure that you are on task and doing math only. All right, guys. Thank you.